Gina Master. Thank you, Mr. Ruiz. In this chapter 1, I will be discussing to you the background of the study, statement of the problem, project objectives, significance of the study, and our research scope and delimitation. The background of the study. Every year in our country, we encounter 20 typhoons a year, and that's the reason why the Philippines is one of the countries in the Pacific typhoon belt having an average of 2.348 millimeters of rainwater per year. Residential water use exceeds 400 liters per capita per day, and almost half of it is used for watering lawns and gardens, and the remaining for flushing toilets, bathing, and washing cars. This means a small fraction of water consumed is for drinking and sustaining human life. The application of appropriate rainwater harvesting technology can make possible the utilization of rainwater as a valuable water resource. Typically, a rainwater harvesting system would consist of a catch basin, filter, pump, and a tank for storage. This type of setup would reduce the tap water consumption, and also it would be a great project for water conservation. Next, statement of the problem. The researchers sought to design a rainwater harvesting system, the school building or Dorata building map. The study focus is to provide a solution on how to solve the short demand of water. Second, the design and process that can be used in the rainwater harvester. Third, the volume of the rainwater potentially harvestable from the roofs and the volume of to be treated and seizing of water storage tanks. The last, also one of the studies focuses is what will be the effects and benefits when the rainwater harvester is installed in the school building. This will show the efficacy of the project. Next, the project objectives. The general objectives of the study is to design a rainwater harvesting system in the school building, and also to focus on the following specific purpose. First, to identify and evaluate the process or method used in the rainwater harvesting. Second, to examine the impact and or effects of installing rainwater harvesting system. Third, to implement the solution to the problem or on scarcity of the water, and thus to reduce the loss of water by running off and to avoid. Next, the significance of the study. The rainwater of the collection provides an alternate source of water. It encourages efficient water use. Humans commonly use tap unfiltered water for a variety of the reasons that can also be accomplished using rainfall. With this, the researchers can be ensured that making the best use of this natural resource while also limiting the waste that occurs on the daily basis. As a result, it's critical to employ this technology in order to ensure that we do not run of this valuable natural resource. The significance of the study is to prepare for the not future effects of the rainwater harvester in the school building. To the student of the Bachelor of Science in the Civil Engineering, this will allow the students to know and understand the published works in this area or field of engineering. To the school or Danita City or the local government, doon pwede naman ibalik na lang, tapos i-slice. To the school, Urdaneta City University, and the local government unit of the Urdaneta City, this proposed modern design, rainwater harvesting system can also be applied or used to building of the school or in the city. To the researchers, this will be enable them to identify and evaluate the circumstances of the proposed modern rainwater harvesting and to know how effective their proposed system is. To the future researchers, this study could serve as a guide for the future researchers that maybe have relevance for to this study. This also opens to other researchers to develop and modify the project that can help in enhancing the abilities of the system to perform more functions. Next, The scope and the limitations. The rainwater harvester will focus on the method for collecting and storing rainfall that fall upon the roof. Rainwater can be utilized for non-potable requirements such as flushing, landscaping, irrigation, etc. This system will show its capability to supply the demand of water needed in the building. Also, it will show the impact and or effects of installing a rainwater harvesting system in the school building. Furthermore, the study is constricted only to design a rainwater harvester. This study has the following limitations. First, the harvested rainwater will be incorporated as a non-potable water use only. This is due to the safety health requirements for drinking water. The system will not operate in the summer season where the rain is rarely available in that season. Third, the consumers need to sustain the cleanliness of the rainwater harvester. And last, the storage capacity for the rainwater harvested is limited. The next presenter is Miss Civiliana.
Thank you, Mr. Kasuko. I am Cheryl Sevillana and I am going to present Chapter 2. So, in this chapter, I will be discussing the review of the related studies in foreign studies. First is the jar rainwater harvesting system. So, this study focuses on the country of Thailand, which is located in the world's tropical zone with annual rainfall ranging 102 centimeter in the northeast to over 380 centimeter in the peninsula. The rainy season is from May to October when southwest monsoon hits the country. The construction of over 10 million 1 to 2 cubic meter forest jars for rainwater storage has demonstrated the potential in rainwater cut lang dun. The construction of over 10 million 1 to 2 cubic meter forest jars for rainwater storage has demonstrated the potential and suitability of the catchment system as a primary rural water supply technology. Rainwater harvesting jars are virtually always used by all the individual houses, ensuring that they have clean water all year. The jar range from 100 to 3,000 liters and equipped with a lid, faucet, and a drain. So the most common size is 2,000 liters, which cost 750 baht. Convert it in peso is around 1,140 and holds sufficient rainwater for 6-person household during the dry season, lasting up to 6 months. Next is the rainwater harvesting system in Australia. So this study focuses on urban areas in Australia. Rainwater harvesting is Australia's third primary water source after surface water like dams and groundwater. Rainwater harvesting provides 274 billion liters per year, according to independent estimates. According to the ABS or the Australian Bureau of Statistics, 1 in 4 or 26% of Australian houses have rainwater tank. And according to the Australian Bureau of Statistics, rainwater is estimated to provide 177 billion liters or 9% of estimated residential water in Australia worth $540 million. And outside of urban areas, rainwater provides 63% of residential water or 109 billion liters. Rainwater harvesting is the first and most effective component of an integrated water management system because rainwater is local resource that may be gathered when required since it falls on roofs. Rainwater usually of good quality and it can fulfill primary local water demand until it runs out. So in 2016, Combs and Smith estimated that rainwater harvesting and water efficient appliances save 90 billion liters in Sydney alone, which is equivalent to the total capacity of the 1.8 billion desalination facility. So in Australia, rainwater harvesting is the most accessible source of water, even during drought. Rainwater harvesting continues to provide water long after natural catchment have become too dry for stream discharge. Desalinated water is the reliant on natural rainfall, but it does require a power grid, a water distribution infrastructure, and a significant amount of public spending. So move on to the last one is the rainwater harvesting in Germany. So this study also focuses on the urban areas of Germany. The average rainfall ranges between 563 and 855 millimeters. Household rainfall sources are limited to non-potable purposes such as toilet flushing, clothes washing, and garden watering due to severe industrial air pollution. So the main benefit of designing rainwater harvesting system in conjunction with seepage well is that many German cities charge resident an annual rainwater drainage fee, which is waived if rainwater runoff is retained or returned to the ground, resulting in significant cost savings. Grants and subsidies are provided in many German towns and cities to encourage their residents to build rainwater tanks and seepage wells. Rainwater harvesting at Frankfurt Airport. This is the biggest system of Germany, saving around 100,000 cubic meters of water each year. In the year 1993, the system cost 1.5 million. The combination of large catchment areas and simple technologies has proven quite effective, with the capacity to handle 13 million people per year. So a rainwater harvesting system was constructed. The system collects water from the roofs of the new terminal, which covers a total area of 26,800 square meters. The water is contained in the airport basement, where 6 tanks with a full storage capacity of 100 cubic meter have been installed. The water is mainly utilized for also toilet flushing, watering plants, and air conditioner cleaning. Rainwater is collected in 2 massive installations in Germany. Next is rainwater harvesting at Darmstadt Technical University. So the university has another massive rainwater harvesting system. Rainwater harvesting and recycled water have been used to supply the institution since 1993. So the purpose also is for flushing and cleaning. Since the installation of this system, just 20% of the water demand has been met by drinking water, resulting in annual save of 800,000 cubic meters of drinking water. So that is the end of my report, and the next reporter will be Miss Inaldo.
Thank you, Miss Civiliana. In this chapter, we'll be discussing to you the local studies. First is improvement of water supply. This study, improvement of water supply expected with rainwater harvesting system, focuses on the UP Baguio addressing the water problem on the campus written by Roland Rabang, March 12, 2018. Excavations to establish rainwater harvesting facilities are part of the University of the Philippines Baguio's substantial infrastructure initiatives. UP Baguio would have at least 150,000 liters of water stockpiled if these facilities had total capacity. The water will not be used for anything edible, such as drinking or cooking. They will install a vortex filtering system to remove fine sediments from natural rainwater, making it safe to keep. The rainwater is primarily used for cleaning and flushing, particularly in restroom and watering plants. The rainwater harvesting facility will result in cost reductions for both mobile water delivery and water utility bills. On the other hand, institution had made plans to increase its drinkable water supply. A cistern tank with 586 drums is being built near the College of Social Science stairs from the Japanese garden. As an additional water connection was filled for and granted by BWD for UP Baguio, this will receive water pipe in through the Baguio Water District. Jessica Carino, Vice Chancellor for Administration, claims that this will meet the university potable water needs. She went on to say that the 586 drum capacity cistern tank is divided into two portions, each with 293 drums. She stated that one part would provide potable water for the UP Baguio Resident Hall, while the other half would serve the main campus. The endeavor to enhance UP Baguio's water status is part of President Alfeo E. Pascual's administration's strong support for capital outlay. Prof. Carrier stated that it provides a financing opportunity for which UP Baguio appreciates. The UP system supports a large number of infrastructure ideas with finance. This explains why there is so much development going on at the same time on campus, according to Prof. Cario. Next is rainwater harvesting. This related study, rainwater harvesting, its prospects and challenges in the uplands of Talugtog, focuses on small impounding projects SWIPS in Nueva Ecija. Rainwater collecting using small water impoundment projects SWIPS is well known for its environmental and socioeconomic benefits. Rainwater harvesting reduces flood peak discharge runoff volume, force, and eroding power by collecting and storing rainwater in surface runoff in strategic spots within a watershed. Its impact to avoid local floods and large-scale flooding can be realized with great as clusters of small water impoundments. Furthermore, the rainwater saved can be put to more productive and cost-effective uses such as supplemental irrigation and inland fish production. The SWIP cluster in Talugtog, Nueva Ecija is a test case for gaining the momentum needed to pursue a national policy on rainwater gathering with local government cooperation and strong community-based agricultural organizations. A future rainwater harvesting roadmap should examine the following path, putting the local environmental and socioeconomic gains and challenges of Talugtog Nueva Ecija into a national perspective. First, identify critical watersheds. where rainwater harvesting could have a positive environmental and socioeconomic impact. Second, locate prospective clusters of sub-watersheds within a watershed where small-scale detention ponds or reservoirs, such as SWIP, might be established as a first line of defense against flooding during the rainy season and managed by farmers for diverse economic uses during the dry season. Third, encourage private sector participation in rainwater harvesting programs through strengthening local government participation. Fourth, to gather support and advocacy from all sectors to increase public awareness through education programs. Fifth, create a monitoring system to determine the long-term environmental and socioeconomic effects of rainwater collections using the novel paradigm of clustering SWIP within a watershed as a new development direction. Next is analysis on rainwater harvesting system. In this related study, analysis on rainwater harvesting system as a source of non-potable water for flood mitigation in Metro Manila. Cyclonic occurrences are common in the Philippines. They bring a lot of rain, which causes floods in the heavily urbanized region of Metro Manila. Despite receiving less rainfall during by and medium years, it is still possible to harvest a large volume of non-potable water. During wet rainfall years, however, the amount of rain was excessive. The usage of RWHS could reduce the amount of water extract and Angat Dam and the amount of surface runoff that causes flooding. The use of RWHS can solve the fundamental difficulty of finding an alternative source of water supply. Rainwater is free. Metro, Metro Manila receives a lot of rain, and it's soft water with no hard metals, so it just needs minimal water treatment. Rural regions without access to a water supply can use the RWHS to have safe and unrestricted access to water. Because groundwater accounts for 2% of Metro Manila's water consumption and some parts of the city are located near a lake or the sea, saltwater intrusion could be a significant problem. As a result, runoff can be injected into the ground or retention basins can be used for groundwater recharge to help mitigate the problem's consequences. To use rainwater collected for non-potable purposes, it must first go through simple water treatment to eliminate inorganic pollutants such as filtration media, activated carbon, or sand filtration. While disinfection of the harvested water is required for potable water usage, such as drinking or laundry, it can be accomplished by subjecting the water to UV or chlorine treatment, depending on the primary purpose of the consumer. Rainwater storage might range from a small tank to a massive cistern tank. Because specific data was not available, the sizing of rainwater harvesting storage was not included in this study. To, be bet- to better use rainwater, the Philippines government should encourage citizens to install rainwater collecting system in flood-prone, densely populated areas and in rural areas where neither groundwater nor municipal water is available. Future studies on storage sizings should be conducted to obtain efficient and realistic rainwater storage based on household situations since this study mainly focuses on estimating rainwater capture for Metro Manila. Next is the review studies and the present study compared. The related studies reviewed provide extraordinary insights of the current research because they contributed the researchers on appropriate background. All the local and foreign studies reviewed were similar to the current research in terms of procedure use. Rainwater harvesting system has been practicing all over the world thousands of years ago. Other countries use large vessels to collect rainwater and some use cistern and large tanks. There are different ways to collect rainfall. Tribes, for example in Thailand, collect rainfall directly from the roof and it will be used on basically for their cooking since tribes don't use filters to remove debris from the roof. On the other hand, rich countries collecting rainwater for their water consumptions like irrigation, laundry, washing dishes, washing cars, and for non-potable and potable use, since they use filters and chemicals to eliminate contaminants. Rainwater harvesting system and institutional building collects rainfall from the gutter of the building and will be passed through a series of filters to eliminate debris and contaminants. Rainwater will be stored in a tank for non-potable use. Compared to the previous studies, our project used a, a series of filters to remove contaminants. Using rainwater harvester will be great project to reduce surface runoff and especially water bill. And the next presenter is Mr. Anthony Ruiz.
Thank you, Ms. Doris Inaldo. In this chapter, I will be discussing our research abstract, introduction, conceptual framework, research methodology, research design, the plans and sections of the rainwater harvesting system, and the tools and materials used in survey and constructing the rainwater harvesting system. There has been growing interest in the use of rainwater harvesting systems in recent years. Rainwater can be collected and stored to supply a range of non-potable domestic uses. In this study, the reliability of using rainwater harvesting to cover water demand on school building has to be determined. Rainwater potentially to be harvested from the roofs was estimated based on statistical data of the rainfall. Based on the data to be gathered, potential water saving will be determined. Characterization of rainwater was carried out to determine the process of flow for each water source. Additionally, the capacity of water storage tank was estimated. For the selected treatment systems, an economic assessment was conducted to determine the viability of the alternative proposed. Rainwater harvesting has been proven to be the most economical and environmentally friendly method. The principal objective of this study is to design the rainwater harvesting system as an alternative for water demand in schools building. To transform the school building with green initiative by effective utilization of water resource. An integrated study on rooftop stormwater runoff for qualitative and quantitative analysis was conducted. These findings can significantly influenced by the similar rainwater harvesting initiatives in various government and private establishments for sustainable water management. Rainwater harvesting is a technique for collecting and storing rainwater from rooftops, land surfaces, and rock catchment using simple devices like jars and pots, as well as more complicated devices like subsurface check dams. The techniques used in Asia and Africa are derived from ancient civilizations practices in these locations, and they are still used as a primary research of drinking water in rural areas. The catchment area, the collection device, and conveyance system are the three main components of most commonly utilized system. Rainwater harvesting is environmentally friendly as harvested rainwater may be used for irrigation, laundry, processed water with additional treatment may be utilized as drinking water as well. The most basic version of the technique collect rainwater in simple jars at the roof edge. The collection of rainwater in gutters that drains to the collection vessel through downpipes built for the purpose, and the diversion of rainwater from the gutters to containers for settling particulates before being conveyed to the storage container for domestic use are two variations on the basic approach. The most the amount and quality of rainwater collected relies on the area and kind of roofing materials because the rooftop is primarily catchment region. Roofs made of galvanized coagulated iron, aluminum or asbestos cement sheets, tiles, and slates can collect somewhat pure rainwater, though thatched roof links with bamboo gutters and arranged in suitable slope can produce nearly the same quality of runoff at a lower cost. Our conceptual framework. The research study has a conceptual framework and is presented below. Delineate the input, the process, the output. The figure shows the organization of the main idea required in the study and testing of the performance of the rainwater harvester. In this study aims to contrive a rainwater harvester and a flood controller to eliminate or to evaluate its effects in the school building by conceptualizing the sustainable solution and prevent the problem in this study area. In selecting the materials for the rainwater harvester and flood controller, availability and cost will be set as basis. Later that, the materials will be collected and constructed. The test the performance of the rainwater harvesting system, the researchers planned and designed the rainwater harvested along the roof of the Rata Building 1 within a month and the water consumption will calculate. Our research methodology surveyed Orata Building 1 in Urdaneta City, found out that they have scarcity on water. The researchers plan and design a rainwater harvester in Orata Building 1 in order to solve the problem in scarcity in water. This part of the chapter will determine the plan of action we make in this research. The figure below shows the project methodology of the study. First is the project identification. This part is where the researcher plans what the study is. This part also includes the problem identification and the solutions to the problem in the study area. The researchers go and investigate in the study area. Next is the assessment of the project. This part determines the relevance and the level of achievement of the project objectives and the influence of the project in the study area. The researchers measure the possibilities of the project. Next is the gathering of data. This is where all the data concerning the project gathered using surveys, computations, observations, and documents or records. The researchers gathered data in internet, in the barangay, and in the municipality of Urdaneta City. The research design is the part where the project is structured, for example, the plans, section, and schematic diagrams is also shown, data about the computations and materials used in the project. The researchers draws the project plans, sections, and the schematic diagram. Next is the project development. This is the part of the study where the researchers made a simulation to see how the project output and to evaluate its effects and cost on the study area. The research evaluation shows the project output. Through this, the researchers can draw their conclusions and recommendations concerning the project. And lastly is the presentation of the project. In this part, the researchers are required to present detailed data concerning their studies, such as the procedures, developments, and also evaluation of the project to their respective panels. So the PERT CPM or the Program Evaluation Review Technique Critical Path Method for the Rainwater Harvesting System project shows the schedules and the duration of our research project. Research design. This part of the study aims to acknowledge the concept and workings of rainwater harvesting system if it can collect water, filter and stores, and can be used as an alternative and or supply for water source in the Orata Building 1. There are five main components of a rainwater harvesting system. First is the conveyance, storage, overflow, outlet, and delivery. In addition, a first flush diverter can be installed for improved water quality. Before implementing a rainwater harvesting system, it is important to understand and consider the function of these components as well as familiarization of oneself with local plumbing, building, neighborhood, and environmental codes. The limiting factors in most rainwater harvesting applications are the space available for storage, cost, and aesthetics. Several factors must be considered while installing a system, including contributing rooftop area, rainfall patterns, and anticipated usage. So, next slide. So, the average rainfall in Urdaneta City, Pangasinan, Philippines. So, in this table shows the wettest month. As you can see, with the highest rainfall is on October with 299.5 millimeter, and the driest month with the least rainfall is on February with 115.8 millimeter. The next table shows the average rainfall days in Urdaneta City, Philippines. The month with the highest number of rainy days is on September with 21 days of rainfall, and the month with the least rainy days is on April with 15 days. The plans and section for rainwater harvesting system. So these are the gutter downspout details in the Orata Building 1 with a drainage screen to minimize clogging, a 6 inches diameter drainage pipe, and also a 6 inches PVC downspout. And here as shown in the figure is our design for our rainwater harvesting system. We also include a drainage screen to minimize clogging. We also install 6 inches diameter PVC drainage pipe and 6 inches PVC downspout. This is our filter 1 plan with 1.5 and 1.2 meter dimensions. Also our filter 2 plan with same dimension. Okay, next. Our filter 1 and filter 2 section detail. Next is this. Here is our filter 1 and filter 2 section details. And our rainwater harvesting system diagram. Wala kasi ako yung ano. Type. This is our filtered rainwater storage section. And the tools and materials used in survey and constructing the rainwater harvesting system. So we use tape measure, weather thermometer, chalk, map, cement, perforated screen, sand, gravel, deformed bars, metal cutter, metal chop saw, welding rod, PVC pipes, round bar, PVC fittings, motor pump. We use SAER water pump, high quality standard, most advanced production technology. This SAER convertible deep well jet pump is ideal for water transfer irrigation, industrial applications, and more. So this SAER M100 is 1 HP with maximum head lift of 125 meter, which exceeded our school building with a height of 12.8 meter and has a max suction of 14.93 meter, which exceeded our water storage depth of 6 meter. Also, adding the material is red oxide primer and waterproofing. So here ends my report, and our next reporter will be Mr. Garcia. Thank you, Miss. Yan na. Thank you, Mr. Garcia. So, in this part of the chapter, we have the findings where the importance of the outcome in the rainwater harvesting system. So, as we evaluate and analyze the data in the simulation process, we have here the following findings that we observe. First, the usage of water daily in Orata Building 1 is 50.946 cubic meter because of the use of flushing every single second or minute by every single individual that is using comfort room. Next, when installing the rainwater harvester in the Orata Building 1, the rainwater will
become useful instead that it will just fall in the ground. It will be harvested in using the flush all the comfort rooms that will lessen the volume of usage of water coming from the water line of the water district. Next is the testing results. As the simulation results demonstrate how efficiently harvesting and filtering rainwater lessen the bill of the university to the water district. So on the first table, we gather the amount of rainfall of every month in last 2021. So here we have the average rainfall depth of 181.925 millimeters. Next is the area of catchment where it is 768 square meters. We have the constant value of runoff factor of 1. Then next is the volume of rainfall. To get the volume of rainfall, we will use the Darcy's formula. So by as we solve the volume of rainfall of every month, we have here the average rainfall volume of 1,676.621. Next table is the volume of water used in the building. So we used to 339.84 cubic meter as the volume of water used in building in every month. So we have the total volume of water use of 4,078.080. Next is the volume of rainfall collected by rainwater harvesting system. So we solve the volume of every month that will we have the average volume of rainwater saved of 1,533.120. Next table, the economic factor amount without rainwater harvesting system in pesos. So here we have the 3,398.4. So the water bill without using rainwater harvesting system will be 40,780.800 annually. So the next is will economic factors amount savings with rainwater harvesting system. So we have the water bill using rainwater harvesting system. We have the bill decreased to 25,449.600. Next will be the discussion. Volume of water usage coming directly in the water line of the water district without rainwater harvester. So the water consumption in Urata Building 1 is 339.84 cubic meter per month during face-to-face class. The average water consumption annually is 4,078.080 cubic meter. If computed, the water bill will be 40,780.80 pesos. Next is volume of water usage coming directly on the water line using rainwater harvester. So by using of rainwater harvester, it will lessen the usage of water from the line of Ordaneta Water District because rainwater harvesting system will be the source of water for flush in flood sprinkler in Orata Building 1. The water bill of the university will be decreased especially during rainy season. The average volume of water saved using rainwater harvesting system is 1,533.1 120 cubic meter annually. Compared to the first that doesn't have a rainwater harvester, if computed, the water bill will be 25,499.600 pesos. The next presenter will be Mr. Villavito.
Chapter 5. This chapter contains the summary and conclusion and the recommendations for the research work, which is the rainwater harvester on a institutional building. The project study is located at Ordaneta City, Pangasinan. Next slide, please. Summary. We, the researchers, aim for designing a project simulation of a modern harvesting system on a building institution. The project mainly focused making a simulation of a working rainwater harvester. The roof of the building would be the catch basin for the water with an area of 768 square meter. The roof would collect a 1,672.621 cubic meter annually of rainwater that will pass through the PVC pipes as means of transferring the gathered rainwater to the first manhole on the ground for filtration using perforated cylinder. After the first filtration, the water would go to another second manhole for another filtration. The collected filtered rainwater is then transferred to the third manhole for embankment. A 1 HP motor would pump the water to the water pressure tank at the top of the building and ready to be distributed on cubicles in each restroom. Conclusions. We have successfully met the objectives of the project study and concluded the following. First, we researchers designed a rainwater harvester that is a solution to the problem of water conservation in a school facility building. Second, the researchers were able to identify and evaluate the design and process that can be used in rainwater harvester. The researchers were also able to identify the water line design that is compliant to a school facility. Next slide, please. Next slide, please. Third, the researchers were able to determine the volume of water that can be potentially harvested from roofs and the volumes that can be treated for utilizing a potable water. And lastly, we researchers determined the efficacy of the rainwater harvester through the simulation process, from the illustration of the harvesting system to the installation of rainwater harvesting system and to the illustration of the rainwater harvesting system efficiently collecting rain from the roof, filtering and distributing for the school facility. Recommendations. Based on the observation, the data gathered from established sources and the outcome, we recommend that there would be a once a week cleaning on the roof of the building where the gathering of water should be done even when it's not on operation. The dust and other foreign objects would clog the pipes from the roof when not in use. Also, we recommend that the cleaning and securing tanks to keep the insects and small animals must be done to reduce the contamination. Rainwater is attracted to bacteria and other pathogens when the water is stagnant. A staff of the school would need to check the water levels would reduce the risk the stagnant water. And for future research, the excess water for the harvester can be used for refilling ponds and other water bodies. Lastly, we recommend it to the school administrative team with the help of also the students to clean and maintain the cleanliness of the harvester and area around it so it can avoid risk, maintenance, and contamination. That's the end of our presentation. We will now proceed to the next part, which is the questions and other recommendations of our dear panels. Thank you.